everyone, welcome back. In this particular video, we will be discussing the algorithm known as bubble sort. Problem is, given a unsorted array of integers, that is, there are some elements in the input array which are ordered in random order. What you have to do is, you have to sort them in ascending order. And for now, you can assume that there might be duplicates present, there might be no duplicates present, there might be that input elements having any value. It might be negative, it might be zero, it might be positive. But just for the dry run, we will be taking a simple test case. So we can have, after the array to be sorted, the output will be in increasing order, that is ascending order sorting is what we require. It should look like 10, 20, 30, 40, 50. Now the point is, how will you solve this problem using bubble sort technique? What will bubble sort say, or what is the emphasis behind bubble sort? It is nothing but we will compare the adjacent elements one by one, and if required, we will do the swapping in order to make the array sorted. That is, in order to make the array come in ascending order or increasing order. If any pair of adjacent elements we will see are opposite to what they want to be, then we will swap them. Swap them means interchange their positions or interchange the values at those corresponding indices. Let's take the example of 0 index comma 1 index. These are adjacent indices. After array becoming sorted, do we require 50 before 30 in ascending order? No, we will say 50 is greater than 30. It means 50 should come after 30. What do you mean by that is, we will do the swapping in between 50 and 30 so that we are approaching towards a sorted array in increasing order. However, when you compare in between 30 and 40, what will you say? Comparing between these two elements, you will not really do a swap. The reason being 30 is smaller than 40 only, and it should remain smaller in the left hand side. That is, we should not swap these elements. So sometimes we will be doing swappings, sometimes we will not do swap, but we can't just only compare all the adjacent elements only once. We can't have a single pass and say the array will get sorted. We will require multiple passes in order to do it. So let's start the algorithm by the first pass. And what do you mean by first pass? We are going to each pair which are having adjacent indices and comparing whether we should have the swap or not, whether we should interchange the positions or not. So what are the adjacent positions which are available? Either it might be that you are comparing in between 50 and 30. That is the first possible pair. Let's go from left to right. So we will have 50 here, we will have 30 here. We will say since 50 is greater than 30, after array being sorted, 50 should come at the right hand side. It means do the swap between them. Make this value 30, make this value 50, and remaining array obviously will remain same. The remaining array will have 40, 20, 10. This is only the first pass going on. We will have all the pairs. That is now next pair will get compared, which is actually the first index going to get compared with second index value. Only we are bothered about the adjacent indices and swaps between them because bubble sort relies on that logic. So this time what we will do is we will compare first index with second index. That is the values which will get compared is 50 versus 40 because now we have 50 here after the swapping is done. This is 30, this is 20, this is 10. What we will say is 50 is also greater than 40. It again means that 50 should come after 40 and 50 should come after 40. We will do the swap between the first index and the second index value. I hope everyone already knows how to do swaps between two elements of an array. If not, then we will also discuss that logic during the dry run of the instruction manual or during the writing of the pseudocode. So we will swap these elements because we want to sort the array in ascending order. But the first pass is still not complete. There are still more pairs of adjacent elements to get compared. So 30 is present here, 40 is present here, 50 is here, 20 is here, 10 is here. Now is the point we are comparing 50 with 20. That is the second index with the third index. So if you will compare these two indices, what will you say is, again, 50 is greater than 20. Again, we should swap these elements. And if we will do the swap, this will become 20. This will become 50. There is one more pair of adjacent elements which is yet to be compared, which is the third index with the fourth one. First pair was 0, 1. Next pair was 1, 2. Next pair is 2, 3. Now the final pair which we are about to compare is third index with the fourth index. Let me just quickly write the array. This is 30, 40, 20, 50, 10 at this moment. And when you will compare the values present at 3 and 4, that is values 50 and 10. Again, the same thing is what you are about to say. That is, we need swapping because 50 is more than 10. 50 should come in the right side of 10 after sorted array. So make this value 10, make this value 50. After doing the single pass, is the array sorted? As I said, it is not necessary. It might be, but it might not be. And highly likely it is not going to be sorted. Because you can see it is not sorted. It is having 30, then 40, then it is a dip having value 20, then it is again a dip having value 10, then it is having value 50. So there can be any order of values present. What we necessarily need to do is have multiple passes. But there is one very important observation which we can make out of the first pass. And what is that important information? Although the entire array is not sorted, but surely one of the value is at the sorted position. After array getting sorted, what will it look like? It will look like 10, 20, 30, 40, 50. Out of these five values, if you will just compare it with the sorted array, you will see that the heaviest element, biggest value element, maximum element, after doing the first pass is actually at its correct position because it should be at the correct position. This is how we are doing the swappings, or this is how we are doing the comparisons. What we were doing was comparing 50 with 30, making it to the right side because it was heavier, swapping it with 40 because it was more than 40, swapping it with 20 because it was more than 20, swapping it with 10 because it was more than 10. So we are essentially making the heaviest element go to the rightmost side. So 50 at the first pass after the completion of the first pass is already sorted. That is the last index of the array. If array was of 5 size, the fourth index of the array is already sorted. So in the next pass, do we really need to compare four pairs? Do we really need to compare this time 30 with 40, 40 with 20, 20 with 10, and also 10 with 50? The answer is no. We don't require four comparisons in the next pass. In next pass, we don't need to compare with 50 because 50 is already sorted. 50 will not change its position because it is the maximum element and it will be at the rightmost position. So that is the important logic. What we have to just ensure that next pass we will not compare with 50. Even if you compare, the time complexity will not change in big O notation, worst case notation, but still it will be better if you are following the exact same strategy, which is bubble sort. So we will say in the next pass, let's first copy the array, which is nothing but this time 30, 40, 20, 50, 10, and then finally 50. This is the array. But this time what we will do is we will only do three pairs of comparisons. That is 0 with 1, 1 with a 2, and then 2 with 3. No need to compare with the last index because it is already sorted. First, if we compare 30 with 40, will they do the swap between them? Will we swap? Let me just write it a little towards the top. There's a 0, 1, 2, 3, 4. Now we are doing the first pass. Actually, the second pass. This was the first pass. What we will say is 30 is in the left hand side, 40 is in the right hand side, 30 is smaller than 40. It should remain as it is in the output order also. So don't swap. We will compare, but we are not swapping. But since we are comparing, it is still a iteration getting passed. We still require some loop in order to do that. So 30, 40, 20, 10, 50, the array is remaining same. But this time, if you compare 40 with 20, we will say 40 is greater than 20. Yes, we require a swap. This value will become 20. This value will become 40. If you write the next array, it is 30, 20, 40, 10, 50. And now if you will compare 40 with 10, again you will say require a swap. Heavier value on the left hand side should not be there. Smaller value on left hand side should be there. So make it 10, make it 40. And after the second pass, having only three comparisons, we can say 50 was already sorted at the last index. But now after the second pass, the second heaviest element is also sorted. 40 is at the second last index because it is the second largest element that is at third index. So in the next pass, we can't say that array is sorted completely, but at least since two elements are sorted, now next pass will be only among these three elements. The comparisons will be only among these three. That is, there will be only two pairs of adjacents, which we are going to compare in the pass number 3. So what we are going to do this time is, let me first copy this array. This is 30, 20, 10, 40, 50, just the previous array we are using it. It is not copying, it is just I'm doing the dry run. And while doing the dry run, I want it to be as clean as possible. So this is zeroth index, first index, second index, third index, fourth index, where 0 till 2 is only unsorted, 3 and 4 is for sure sorted. So since only two pairs are required, let me just draw those two pairs between 0, 1 and 1, 2. First, you will compare the 0 index with first index. What you will see is 30 getting compared with 20. We require swaps. This should become 20. This should become 30 because smaller element should be on the left hand side. If you will do that swap, now when you will be comparing first index with the second index, you again will say 30 is also smaller than, actually 10 is also smaller than 30, or 30 is greater than 10. Again do a swap, and again doing a swap. What will the array look like now is 20, 10, 30, 40, 50. After the third pass, how many elements are sorted? After first pass, one heaviest element was sorted. After second pass, two heaviest elements were sorted. After the third pass, three heaviest elements will be sorted. That is 30, 40, 50. Last index, second last index, third last index will be having correct elements which will be there in sorted array as well. But is the array sorting done? No, still we have two elements which are not in the sorted order, not in ascending order. So at least we can say that we require how many more comparisons? Since there are two elements, how many comparisons will we do is one comparison in between them. That is in between 0 and 1. So now the last pass will actually only take a single comparison, which we will say is the pass number 4. So let me just show the pass number 4 here itself. What we will do this time is, in this array, if you will compare, let me just actually copy the array, not use the same array. For that, let me make it a little bit smaller, and let's copy the array. This is 20, 10, 30, 40, 50. We can say we will compare 0th index with the first index. And if you will compare them, you will say require sorting, or actually not sorting, but swapping is required. This will become 10. This will become 20. Let me just write it in blue. As soon as you do this fourth pass, you can for sure say one element was sorted after pass 1, two elements were sorted after pass 2, three elements are sorted after pass 3. Are there only four elements which are sorted after pass 4? Yes, there are for sure four elements, but if there is an array of 5 size, out of which four elements are sorted, automatically the fifth element is sorted. There is no other comparisons which we can make for 10. 10 is automatically at the correct position. So we don't really require the fifth pass for an array of 5 size. We only require 4 passes. That is, for an array of n size, we will only be requiring n minus 1 passes for the bubble sort. And in each pass, how much time are we taking? In worst case, it might be n minus 1 comparisons, that are 4 comparisons, or 3 comparisons, or 2 comparisons, or 1 comparison. In worst case, it will be n comparisons or n minus 1. Or even if you just want to calculate the total number of iterations, it will be 1 plus 2 plus 3 plus 4. That is 1 plus 2 plus 3 up till n minus 1. So overall time complexity will be how much? It will be sum of first n minus 1 natural numbers. And if you will just calculate it, it will come out to be n minus 1 times n by 2. But in big O notation, you can simply say it is quadratic, that is n square. In big O notation, you don't take the smaller powers of n. So just by looking the time complexity, you can assume what will be the code looking like. It will be most probably a nested loop. One loop for each pass because there are multiple passes, and inner loop for comparisons between adjacents in that pass, which will start from 0 with 1, 1 with 2, 2 with 3, 3 with 4. So if let's say this variable is I, this variable will be I plus 1. Or if let's say this is inner variable, inner loop variable, let's name it J, and let's the pass variable be named as I. Outer loop, let's name it as I. Inner loop, we will name it as J. That we will do during the dry run of the instruction manual. But the point is, this is about time. What do you think is the space complexity used by bubble sort? We can say if the input array is of integers, we can just directly change the input array itself. There is no need to create a new array. And if there is no need to create a new array, space complexities for sure, constant extra space is required, or constant output space is required, because what we are about to return, the array which we are about to return, will be same as the input array. No new array is used. So such kind of solutions which require constant extra space are known as in-place solutions. That is, we can do the swappings, do the comparisons in the same input array itself. No need to copy the elements, no need to create new data structures. So time will be quadratic, space will be constant, and the time will actually be quadratic only in worst case or average case. If you want to optimize the best case, you can, but that is actually a follow-up. You can just look on your own how to optimize in best case. What will be best case? Hint is, if array is already sorted in input, how will you use that already sorted array to just maybe sort in linear time, not n square time? Because if array is already sorted, you don't have to actually do any swappings. But we are not doing that kind of optimization for now. We can assume that we have to code in worst case only, or we have to just only take care of worst case time complexity. For that, let's write the instruction manual. So I will be writing instruction manual in the sort array function, which will be taking the input array and which is expecting a output array to be returned. Since we don't have to create a new array, we can directly start with the loops. There will be two loops required. Run a for loop for passes over, let's say, index over index I from 0 or 1. If you're starting from 1, till which index? The last index will be, or the last pass number will be 4, which is n minus 1. There are total n minus 1 passes. So start the I loop, that is pass loop, from 1 to n minus 1. Inside each pass, what we are going to do is we are going to run another loop, run a for loop for comparisons, for comparisons over indices starting from 0, because the indexes always start from 0 only. We will compare 0 with 1, 1 with 2, 2 with 3, and last comparison will be with 3 and 4. So if let's say we are using this variable as I, this will be I plus 1. This is I, this is I plus 1. This is I, this is I plus 1. This is I, this is I plus 1. If pass variable, actually this is not I, this will be j, because I variable we have already used for pass. If I was 1, till when is the j running till? You can say it is going till 3. If I is 1, j is going till 3. That is 0, comma 1, j comma j plus 1, 1 comma 2, 2 comma 3, and finally 3 comma 4. So final j variable is 3. So I is 1, last j variable will be 3. We have to find what will be the last j variable till when we should run. If I is 2, that is pass is 2. What is the last j variable? It is only second index. Second index getting compared with third index. So I2, j is also 2. If I is 3, that is pass is 3. What is the last j index? It is nothing but the first index. And finally, for the last pass, I as 4. What is the j? The j is actually last j is only 0. So how you can calculate j using I? Because as you can see, as I is changing, as the pass is changing, the last comparison is also reducing. It is starting from 3, then 2, then 1, then 0. So what is 3? It is actually n minus 1 minus 1. That is, from last index, take the previous one. N minus 1 is the fourth index, take minus 1 from it. What is 2? This is n minus 1 minus 2. From last index, go 2 indices previous to that. What is 1? It is n minus 1 minus 3. That is, from 4, subtract 3, you will get to 1. And what is 0? It is n minus 1 minus 4. So what is minus 1, minus 2, minus 3, minus 4? It is actually minus I itself, minus pass is itself. So the last j variable will be n minus 1 minus I, n minus 1 minus I, n minus 1 minus I, n minus 1 minus I. What we are going to say is, for the inner loop, the j variable, not I, will start from 0, but go till n minus 1 minus I. And inside that, what we have to do is, we have to compare if value at the array of j is more than array of j plus 1, it means the left value is greater than right value. We have to do swapping for ascending order. And if we have to do swapping, we will most likely swap values at array of j with array of j plus 1. I'm not writing how will you swap them, but let's discuss how we can actually do it. Let's say the I and j, or actually not I and j, but j and j plus 1 were 0 and 1. If j is 0, j plus 1 will be 1. Let's say the values present here is 100. Let's say the value present here is 50. We have to swap them. What we will do is, in order to swap two elements, we have to take a third element or the third variable. You can also do it without third variable, but easier one will be using third variable. Let's say a temporary variable where you can store either array of j or you can store array of j plus 1. It is up to you. Let's say we are storing array of j in the temporary variable. Now, since you have stored 100 in temporary variable, you can go ahead and update it with the new value, which should be 50. That is, array of j should get updated as array of j plus 1. And then you can update this array of j plus 1 as 100. But where is 100? Here, 100 is not now at array of j. It is updated with 50. Array of j plus 1 should be updated with temporary variable. Array of j plus 1 should be updated with temporary variable. Where what was temporary variable? It was the same copied value from array of j itself. So these are the three steps in order to swap two elements present at the j and the j plus 1th index. So I'm not writing those logics here, but it is self-explanatory that you have to use a temporary variable, a third variable, in order to swap two values. After this entire logic is done, we have to return the array. So we will return the same input array, return the same input array, which is ARR in this case. No need to create a new array because it is an in-place solution. And that was all about your pseudocode or the instruction manual for the problem bubble sort. We will be writing the code in Java programming language. We were having multiple passes. In each pass, we were doing some comparisons. Outer loop will be for passes for which I am using a variable named as I, starting from some value, going till some value. But when it comes to the inner loop, it is going to be used for the comparisons and eventually the swaps, which we are naming as J, starting from some value, going till some value. And what we are doing inside the inner loop is we are comparing first without swapping. First compare, that is the left element that is at the jth index greater than the right element that is present at the j plus 1th index, just the next index. If it is, we have to swap these values. And how to swap these values? We already discussed it in the approach video. We have to take a third variable, which is temporary. So let's say temporary is storing array of j. Now you can update array of j with the other value, that is array of j plus 1, and you can make the array of j plus 1 get updated with array of j. But where is array of j stored now? It's stored at temp. So you will say we have to update it with temporary. So these are the three steps in order to swap two elements present in array. But only thing which is remaining is the question mark. What is the question marks going to be? How are passes or how many passes are we having? They are from first pass till n minus 1th pass. Because of array of 5 size, we only require 4 passes. So let's start with 1 and let's go till less than n, because less than n will eventually mean less than equal to n minus 1. But when it comes to comparisons, we will always start comparison in between 0 and 1. That is 0 and 0 plus 1. That is, j will start from 0. What is the last index of j? It will be based on the I value, on the pass number. If pass will be first pass, the last j index will be n minus 2. If the second pass is there, I is 2, the j variable will go till n minus 3 and so on. So the last j variable will be less than n minus I, or you can say less than equal to n minus I minus 1. Both will work. So this is the code for the bubble sort in Java. It will most likely be same in other languages too. But since we have to return the output is same as input array. There is no new array which we are creating. We can just return ARR. No need to create a new array for return type. Let's just run this code and confirm whether it is going to work for all the test cases or not. So for that, I am opening a terminal. Let me actually open the terminal for this. And how I can find terminal, let's see. It should come from bottom. So first I will compile the code by using the compiler of Java. And this is actually I'm coding in VS Code. It is an online VS Code inside GitHub. So first we have to compile a Java code by using Java C, then the file name or the class name .java. That is sorting algorithm .java. And then you can, in the same line itself, just run that code by using and operator. That is, do two operations. First operation is compilation. Second operation is execution, which will be done by the JVM, where you can give the command as Java. This time only sorting algorithm, only the name. No need to give the extension as .java. If you will hit enter, what it is waiting for is, actually there are some errors which we have to resolve. Then only we will give some input. So the error is n variable is not declared. What is n? N is the array size. So you can use n as array dot length in Java. You can get it from array's length itself. You can use array dot length in Java. Or you can also pass n variable in the function sort array. It is up to you. But most likely, after doing these changes, if we will run, hopefully it should work. So right now, as you can see, it is not showing any error, but it is waiting for your input. So let's give the same input. First input will be the size of the array, which is, let's say, 5. Now it is waiting for the elements. Elements are 50, 30, 40, 20, 10. Let's give the same array. 50, 30, 40, 20, 10. After sorted, as soon as I hit enter, it should give me the output as 10, 20, 30, 40, 50. Let's see. And we can see the output as 10, 20, 30, 40, 50. Because the input output logic will most likely be given to you already. In interviews also, you don't have to write this logic usually. You only have to write the algorithm, which is this much only. Having said that, what is the time complexity and what is the space complexity of this code? Since we are running two loops which are nested inside one another, both in worst case might run for n minus 1 times. So it will be overall in big O notation order of n square, that is quadratic time complexity. However, as I told in the approach, just take a follow up in order to write this code or add some logic to make the best time complexity to be linear. That is, add some logic to check whether a array is already sorted or not after each pass. But currently, average and the worst case time complexity is quadratic n square. What about space? Since we are just updating the input array itself, there is no extra data structure which we are creating to solve this problem. So it is constant extra space, or you can say it is an in-place solution. With that, we are done with the bubble sort, the code of it. We will meet in a new video with a new problem. Till then, bye bye.